maybe. Okay. So our second lecture in this evening will be Chen Jiang from Fudan University, and his lecture, the title is already on the screen.
Okay, thank you. So thanks for the introduction, and I'm very happy to be here, and I would like to say happy birthday to Professor Shokov. So
thank you.
So it's my honor to talk in this conference online. So it's a pity that I could not attend it in US. So hope we can meet in person sometime. So today I'm going to talk about something. It's like a classical topic. It's about the inequalities on the intersection numbers of divisors. So let me record the. Okay, so here I'm working on any algebraically closed field, so of arbitrary characteristic. So let me recall the following the Khovanskii Teissier inequality. So it's proved by Teissier and Dynamical in the analytic setting, and later, I'm not sure who proved first, but it appears in the last field book. So the positivities. So it's says the following. So say X is a projective variety or a compact Calabi manifold of dimension n, and we consider two divisors, two knife divisors or two knife classes, B and C. Then we consider the intersection, b to the k times c to the power n minus k. Then this intersection number has a lower bound, which is just estimated by the self-intersection numbers of B and C of the certain power. You can imagine that. So this is like the log concavity of the intersection numbers, right? So and also we know that when equality holds, say for example when B and C are big, especially these two sides are non-zero, if and only if they are proportional. So this is this is just for example, if n equals 2, then it says nothing but the Hodge index theorem, right? So and also I think the proof, if we are familiar with the proof, I think is consequence of Hodge index theorem. You just do inductions. It's not so hard, So then, as my title suggests, we are interested in the so-called reverse version of this inequality. That means we want to study the upper bound of this intersection number, not the lower bound, but the upper bound. And here is, so I will first give you the statement of theorem. So we call it the reverse Khovanskii Teissier inequality. So it was first proved by Lehmann and Xiao in like 5 years ago. So they proved it in the analytic setting. And last year, Zhiyuan Li and myself, so Zhiyuan is a colleague in Fudan University. So we proved the algebraic version. So it says the following. So let's consider X, the same setting. X is a projective variety or compact Calabi manifold of dimension n. And we take three NAF divisors, A and B and C, NAF divisors or NAF classes. And then the inequality is the following. So we consider the upper bound of this intersection number. It was bounded by intersection number of this form. So this is just the binomial number, right? And we estimate this number by intersect A into this intersection number. Right? So if we want to bound the intersection number of B and C above from above, so you replace B and C by A with this form, and then you divide the self-intersection number of A. So this is this is the form we call it the reverse Khovanskii Teissier inequality. Of course, here I assumed this self-intersecting number of A is non-zero. Otherwise, this inequality is trivial. Okay. So also we currently we cannot characterize the equalities. So maybe I will discuss this in the end of the talk. But we can see that so if A and B and C are all ample, then this equality is actually strict. So it will never happen that so the equality will become I'm sorry, this will be the inequality is strict. So if A and B and C are ample, so then it will never happen to be equality. Okay, so maybe so this form looks not so so I mean, how to say it looks complicated, but let me explain why it's natural. So say when k is equal to 1, so the simple case, when k is equal to 1, we can rewrite this inequality as this form. So it's the intersection of A with, so this is just a one cycle, right? You imagine c to the power n minus 1 as a one cycle. Then it says that the left-hand side is bigger than the left-hand side. And if you write it in a linear form, you will see that this is almost equivalent to this form. So if the right-hand side is bigger than 1, so it's the self-intersecting number bigger than this one, then the left-hand side is bigger than 1, which means that actually A minus B is B. Okay, this so all pseudo effect, this is almost the same. So it means that A minus B times the movable curve, right, is positive. Okay, so then I think many of you know this form, right? So it's I think it's used in many places. For example, you can find this form in Lagerfeld's book, or when proving some non-vanishing result of the divisors, you match this. So here the assumption is A and B are F. Okay, so then this is actually an easy consequence of the Lehmann formula. I think this is a good exercise, and everyone can do it in like 10 minutes, right? So it's a consequence of Lehmann. Yeah, but the problem here is that in higher dimension, I mean, when k is bigger, then we don't have such kind of interpretation. Like we need to prove. So we translate this problem, this inequality, into something like the global sections of divisor, right? So it's more like we need to translate it into some non-vanishing of cycles, but that will be more difficult. Okay. So then, let me give some remarks. So we want to show this inequality, and actually this constant. So here you can see the binomial number, right? This binomial number is optimal, and the example in your mind is quite easy. So you just think of the product of projective spaces, and you take B and C to be the pullback of O1 from both sides, and you take A to be the B plus C, and then you can easily compute that both sides are just 1. Okay, so then so that means we can take the equality in some time. But also this kind of example also predicts that so when B and C are ample, then this inequality may be strict, right? So our example is the fibration case. So this gives some hint that when B and C are ample, this can be strict. But if you take limits, then it becomes inequality. Becomes not strict, right? So also, so there's some attempt to prove this in the algebraic case. So it's by Dang, and he actually proved this algebraic version of this inequality, but his constant is much bigger than our the optimal one. So his constant is like this n minus k plus 1 to the power k. Actually, what he did is he treat so the idea is similar to what I said when k is 1. So he treat this c to the power he treat this b to the power k and n to the power k as cycles, and he proved something like when the cycle is movable, then we have certain inequality, but the constant is not so good. Okay, and also let me mention about the proof of Lehmann and Xiao and why it doesn't work for algebraic case. So actually, their proof use it. So they solve the Mon Ampere equations and by the Calabi Yau theorem. So actually, what they did is they by solving the Mon Ampere equation, so they found some matrix locally, and they prove the local version of the inequality, and then you can know that the globally is an inequality. But of course, their proof depends heavily on the Calabi Yau theorem. And when I first saw this, actually last year I invited Xiao to give a talk in Fudan, and so I asked him whether there's a algebraic proof, but he said no. So then we start to consider, as we can see that when k is 1, then this is just by Lehmann rule. So it has a very simple and nice algebraic proof. So we start seeing to give a purely algebraic proof, and then actually we can show it. So in this talk I'll explain the proof. So the main ingredients is we use Okounkov bodies to translate this problem to some to the geometry of Okounkov bodies, and that makes us to prove it in algebra case and actually over any field of algebraically closed field. So also here I want to say something about the method of ours with Dang. So here, as I mentioned, so he treats the inequality, the divisors, I mean b to the power k, as cycles. But actually, this is not, as far as I can see, this is not the right way to consider it, because as we all know, the theory of cycles is much more complicated. So what we did is just we view it as the divisors, and then we use the theory of divisors, which is much easier to handle. Okay, so this is the main theorem. And before I go to the proof, I want to explain some applications of this inequality. Okay, so the first application is a Bezout type inequality. So say we have a projective variety X, and we fix an ample line bundle as a polarization, and we consider some knife divisor classes on X, and we associate some positive integers, and the sum of them are smaller than the dimension, at most of the dimension, and then we choose some subvariety in the self-intersection of the knife classes, and we assume that they intersect properly. And then what we can do is we can estimate the upper bound of the intersections of this subvarieties. So the inequality is like this. So we consider the degree of the proper intersection of y1 to yr, and it's bounded by some constant times the degree of each of them. So this is this looks like the classical Bezout theorem, right? Classical Bezout theorem, it's just we take H and maybe A1 and AR is just a multiple of H, and X is the projective space, right? And we can get some equality by saying the self-intersection number of them equals to the time of degree. But here we have different divisors, right? And this is actually first observed by Xiao in the complex Keller manifold case, so in his proof the constant I marked as red, so it's bigger. So here actually we can show a smaller constant, and by applying our algebraic version of the inequality, we can show this inequality. But on the other hand, we don't know whether whether this constant is optimal. But I think maybe not. It's too it's still very large, but we don't know how to improve it. Okay, maybe some in some special case it should be optimal, but in general I don't know. Okay, so this is the first application. And the second one is the application on the so-called dynamical degree. So say we have a projective variety with a naive and big line model X H on X, and we have a rational self map, a dominant rational self map from X to itself, and then we can define the degree of F with respect to H is like some intersection number. It's so here pi1 and pi2 are the projections of the graph of F to the first and the second component of this X cross X, and that means we just resolve this we resolve this map, and we pull back the certain intersections of a certain power of H onto the resolution, and we take the intersection. Okay, so then we can show a degree inequality. It's like this. So say if you have two rational self maps, and then we can estimate the composite of them, and with the degree of both of them. So it's like the degree of the composite is smaller than the product of the degree of each of them with some fixed constant. So this constant is independent of F and G. Okay, so this is actually first proved by Dang in with a weaker constant. So here it's maybe like n minus I plus 1 to the power I or something. Yeah, by the weaker inequality. But by our inequality we can just modify this. But of course we don't know if this inequality, I mean, if this constant is optimal. But actually, yeah, the optimalness is not important. The existence of this constant independent of F and G is important. Oh, sorry. So it's actually essential to define the so-called dynamical degree of a self-rational map. Okay, so this is two application of our inequality. And then let me move to the proof. As I said, we prove this inequality by the Okounkov body. So let me just briefly recall what is Okounkov body of a divisor. So this is we follow the paper by Landersfield and Musata. So say given a projective variety X of dimension n, and what is the admissible flag? So it's just a flag with with some subvarieties x1 to the xn, where xn is a single point, and each xi is a irreducible closed subvariety of x of codimension I. Okay, and we assume that so they are both. So actually, in original context, it's assumed that this all varieties are smooth. But actually, we only need to assume that they are all smooth at this point x. It's okay. And then we can define for divisor d on x, so a big divisor d, we can define a valuation-like function of the in the Q linear system of d. So to r to the power n. So it's defined as the following. So what is nu one? Nu one is just the coefficient of x1 in d prime. So given a d prime any d prime in the Q linear system, and then we just remove this x1 from d prime to be d1. And then what is v2? Then we just restricted this d1 prime to x1. So because so it has no common component, then the restriction is well defined. So then we calculated the multiplicity of the restriction, multiplicity of x2 in this restriction, right? So inductively, so we can each time we just calculate the multiplicity, and then we just remove, we remove the corresponding divisor, and then we take restriction and we can compute the multiplicity. So this is like a inductive procedure to define these numbers. So it's very like the multiplicity. Okay. So here, so I should remark that so although we don't assume that they are the smoothness, but everything we do is over the generic point of every xi. So then so the divisors and the multiplicity, they are all well defined. So we don't need to worry about the smoothness. Okay. So given these values, then what is the Okounkov body? So it's just so we take all the valuation, I mean these values in r to the power n and run over all the divisors in the Q linear system. So then they are like points in the Euclidean space, and we take the convex closure of it. Then this is a Okounkov body of the divisor D. Okay, so then so what is interesting is that this Okounkov body of D, it shows many geometry of D, many properties. But what we use is just the following. So we know that the volume of the this convex body. So as the Minkowski of volume of the convex body is just the volume of D up to a scalar. Okay, so this kind of we use this kind of result. So it's for any admissible flag, this equality holds. So that means you can compute the volume of D by drawing the picture of Okounkov body. But of course, in general, it's very hard to compute the Okounkov body. So it doesn't make the computation easier. But we have this nice correspondence. Okay, so let me just give some example to in dimension 2. So in dimension 2, so we just have x0, x1, and x2 as a point. Okay, so then the picture is as the following. So this is the Okounkov body. It starts from v1 equals to nu1 equals to a from a0 to a1. Here a0 is just the the multiplicity of x1 in n0, which is the negative part of the Zariski decomposition. And A1 is just like the pseudo-effective threshold of x1. Okay, so you can imagine that the new one should inside this interval. Okay, and then what is the value of new two? So for any t, so the new two should take values in an interval from alpha 1t to alpha 2t. So here alpha 1t is just the order of x. So this x is just the point of x2. So the alpha 1 is the order of x in the nt restriction on x1. So here pt and nt is just the Zariski decomposition of d minus tx1. Okay, and alpha 2 is just alpha 1 plus the intersection number of x1 times pt. Yeah, of course, here the boundary is not linear, so it should be piecewise linear. But to draw the picture, I just draw it linearly. Okay, so it depends on the jumping of the Zariski decomposition. So it should be piecewise linear. Okay, so this is not actually not so hard to compute. Okay, so let's go back to our inequality. So how to translate it into a problem of Okounkov body? So we can just rewrite this inequality as the following form. So just the b times c, and we just you use these numbers. We give these numbers to the certain intersection number, and then you can see that such kind of thing looks familiar, right? So it appears on the right hand side of the volume equality of the Okounkov body and the volume. And so then we just rewrite these three as some volume of Okounkov bodies. So say for simplicity, let me assume that here B and C are very ample. Then we can take very general complete intersections of C and B, right? So we just write it as Z and Y. Then this one is just the volume of A restriction on Z, and this one is just the volume of A restriction on Y. Okay, so then we can just rewrite it as the following form. Right? So then this annoying constant disappear. It just becomes just some constant times the volume of the Okounkov body on X with the Okounkov body on Z and Y. These certain Okounkov bodies. Okay, so then let's forget about this red constant for a while. So it basically tells us that we need to compare this Okounkov body with the cross of these these Okounkov bodies, right? We can view them as in a same Euclidean space, right? So if we can say something like this Okounkov body is contained in the cross of these two, then at least we can show that without this red constant, the inequality holds. Yeah, actually, this is what we first proved. So we just take the projection of this Euclidean space to Rn minus k and nk. So this is the projection to the first k coordinate, and this is last projection to the last n minus k coordinate. Then actually we can introduce admissible flag like this. So we take x to be x0, and x1 to be just a b, and x2 to be the b intersection, the complete intersection of b. Okay, and then xk is just a 1. Xk is just a y. and then we just take a admissible flag of 1. Then this admissible flag is naturally induces a admissible flag of 1, right? And also it induces admissible flag on Z, by which we just intersect the first k part with C, and then we get from Z to Z1 to ZK. So here Zi is just the intersection of X with C, but for ZK we just take 1 point. Okay, so then we have three flags. Then the claim is the following. So if we project the Okounkov body of X to the last n minus k coordinate, then it's just contained in the Okounkov body of Y, of D restriction on Y with this flag. And if we project the Okounkov body to the first k coordinate, then it's just contained in the Okounkov body of Z restriction on Z, D restriction on Z. Okay, so let me explain the proof. Actually, it's not so hard. Actually, it's not so hard. Say we want to prove. Let me explain the proof of second one. The first one is almost trivial. So actually, the second one is also easy. So say given some D prime with the value nu1 to nu n, we want to show that nu1 to nu k is a point in this Okounkov body, right? So we just recall the definition. So we take nu1 to be the multiplicity of x1 in D prime, and we just subtract x1, and then we take each step. We just take inductively. We take the multiplicity of x I plus 1 of the restriction, and we subtract the certain multiple of the x I plus 1, and we can define the nu1 to nu k inductively in this sense. But here, as we take Z to be very general, then anything, if we restrict D prime to Z, then all this multiplicity just preserved, right? So actually, we can just rewrite this formulation, but everything is on the restriction of Z. Okay, so then all the numbers preserved. So that means if we want to compute the values of D prime restriction on Z on the flag Z naught, so it's actually just this nu1 to nu k. So that means that this nu1 to nu k is inside this Okounkov body. Okay, so here I should say one sentence about the very general Z. So at the first the choice of Z it depends on this D prime, right? But and also this D prime in the linear system is uncountable. But to determine the Okounkov body, you can just look at its rational point. And so actually the Okounkov body is determined by rational points. So it's determined by countably many D prime, right? So countably many D prime. So then we can choose very general Z to say that this equality holds for all the countably many D prime we consider. So there's no problem to choose a very general Z holds for all D prime. So then we can show that this 1 and 2 holds. Especially we can show that, oh sorry, so here should be D, right? So the how to say, the Okounkov body of D is contained in the product of the restriction of D to Z and Y. Okay, so this inclusion holds for the special choice of this X naught. So we choose it by taking complete intersection. Okay, so then we can show that the volume, right? So the volume of it is smaller than the product of the volume of both sides. But this is not the end, because as you may remember that we ignore this the red constant, right? So actually the proof looks very nice, but the problem is something is missing, right? So we missed this red part. So then let me explain why what is missing. What's missing? So recall that in the construction of Z naught, so we just choose Zi to be the intersection of Xi intersect with Z for I smaller than k, and we choose Zk to be a point. So this is because in the original definition of a Okounkov body, so the last zero dimension variety, it must be a point. It cannot be like a set of points. But by doing this, we lost many information. Yeah. For example, go back to the proof of the last claim. So in the last step, actually we have this information, right? So the dk minus 1 prime restricts on k minus xk minus 1. The coefficient of sk is nu k in this divisor. And this is the definition of nu k. And then by restricting on z, what we get is actually the restriction of this divisor is bigger than the nu k times a set of points. And then we just choose one point. So by doing this, actually we lost the information in the middle. So actually in the middle, there are like n points where n is just equal to this red number. But we just throw n minus 1 of them, and we keep 1. And by doing this, we lost many information. Okay, so then actually, so the correct way to think of it is just instead of constructing this flag end with 1 point, we need to construct the flag end with actually with this n point. We need to keep the information of the xk intersects z, or all the set of these points. Okay, so then to do this, we need to find a new find a modified version of Okounkov body and find some relative related inequality on the related equality on the volume. Okay, so this is here we introduce the so-called multipoint Okounkov bodies. So this is due to Zhiyuan Li. So here I only state a simple version. So say a multiple point in the middle flag is just a flag which we allow that the last zero-dimensional variety to be a set of point. So z1 to zk minus 1 is just a variety, sub-varieties, but the last one is a multiple, a set of point. And then for big divisor D, then we can define actually n functions. So that depends on the pj we found, right? So here z naught pj is just the Euro admittable flag n with pj. And then each pj gives us a valuation valuation-like function. Okay, then we take the subset vg in the Q-linear system to be the all the d prime on which the new z naught pj is the smallest one. in the Lex order oh yeah. So the valuation of z prime over the point pj is the smallest one compared to the other pi. So this set, and then we define the multipoint Okounkov body to be the convex closure of this Vg of the value of the Vg in the Euclidean space. Okay, so then actually we have we have n point, then we have n bodies, right? So we have n bodies, and this is like somehow it looks like the subdivision of the Euro Okounkov body. We just take n points and we divide the body. We divide the linear system with respect to the value on different points. Okay, so actually it proves that the volume of the sum of these bodies is the same as the original volume of the divider with a scalar. Okay, so this is actually all we need. All we need to about the multipoints of Okounkov bodies. And then what we do is just so the first claim is preserved, and second claim is that we compare the projection of the Okounkov body with the multipoint of the multipoint Okounkov body, and we can show that if you project x naught to the first k coordinate, then it's contained in this multipoint Okounkov body. So it's like we need to perturb D by ample divider, but it's a very small ample divider on Z. Okay, so we have such kind of inclusion, and then we can finish the proof. So say we want to show that this number, we want to bound this number from above, and this number is just so here n is the intersection of y and z, so n times the volume of Okounkov body, and then each Okounkov body is smaller than the product of two Okounkov bodies on z and y, right? So here the summation comes from this projection holds for any j, and there are n of them. Okay, and so then we can we use the volume equality on the Okounkov body and the divider. Okay, so then we have this one is just the volume of D plus delta A, and this one is just the volume of D restriction on y. Okay, and then as this projection holds for any delta, so we can take delta to be 0. Then by the continuity of volume, then we get this inequality, right? So then the volume of D is bounded from above by the volume of D restriction on Z and D restriction on Y up to some constant. Right, so this is the proof. Also, so in this step, you can see that we are, because we are taking limit, so it's very hard to determine the equality case, right? So that's one of the reasons that we cannot say when the equality holds, then what happens to D and Y and Z. But anyway, we have this inequality. Okay, to summarize, what we showed is the following. So we take so B1 to BK and C1 to C minus K to be very general, very ample dividers. So here by very general, I need to assume that the base field is uncountable. Otherwise, it makes no sense to take very general one. And then we take y and z to be the complete intersection. And then what we showed is that the volume of the restriction on y and z is bigger than the volume of D itself times the intersection of y and z. Okay, so this is what we proved. And actually, it proved it also holds for the so-called restricted volume. So say, yeah, maybe I have no time, so I don't explain this this definition. So, but if you replace the volume x, this volume y and volume z to be some restricted volume on some bigger ambient space, then this inequality still holds. Okay. Then so by this we can actually show the intersection of left dividers as we wanted. So this is just so the intersection of B and A and the intersection of C and A, the multiple of them is bigger than the volume of A times the intersection of B and C. Okay, so for this, so for the intersection, we don't need the field to be uncountable because we can always base change it into a bigger field, right? So as you can see that we first show the first theorem, and then we prove the second theorem, which is a special case. But actually, we can recover the first theorem by only the intersections, because we can estimate the volume of big dividers by ample dividers, right? So actually, you can recover the second one to the first one. So this is some remark I want to say. Okay, so then in the end, let me discuss a little bit about the inequality case. So as I said, we can show that when all the dividers appearing in the inequality is ample, are ample, then this inequality is strict. But I'm not sure if this can be released to only assuming A, B, and C to be big. Yeah, actually, in the proof, we need at least sum of B is ample. Then the inequality is strict. But also, of course, it's very interesting to see whether we can get some characterization of the equality case. So, for example, for surface, it's very easy. So here, yeah, well, let me explain. For surface, when the ABC are left dividers, and then the equality holds. So here I assume that both sides are non-zero because otherwise it's not so interesting. So when the equality holds and both sides are non-zero, then if and only if that A is just expanded by B and C in the non-theoretic group, and also B and C are naive classes with zero self-intersection, which intersect non-trivially. So this is like a baby version of the equality case, and you can see that it looks like the equality only happens when X is like a product type, I mean introduced by B and C, right? And A is just the spanned by B and C. I'm not sure yet if this is the only case happen in higher dimension, but maybe it is. But in higher dimension, it's yeah not so easy to get such a result. Okay, so I think my time is up. So I will stop here. Yeah, thank you for your attention.
Thank you. So any question for Chen?
So can you characterize the equality if you fix K, or like K equals 1? Is that easier or something like that?
Actually, I don't think so. I think if K is 1, I'm not sure, but I don't think so. Yeah, it becomes, let me see. Yeah. I don't know actually. So, but I think it should be easier. I mean, if you consider K is 1, but currently I don't have a solution. Yeah, it's also related to the problem here, right? So if you look at the proof of the case 1, yeah, it's something like you need to consider the boundary of this argument. Yeah, but somehow when considering equality case, somehow we need to treat the movable cycle classes, not only dividers but also cycle classes. But that seems not easy to handle, I think. Yeah.
So if you have a vector bundle, which is a direct sum of line bundles, then the Chern classes of the vector bundle as a whole is equal to all of the Chern classes are the elementary symmetric functions in the line bundles, in the first Chern class of the line bundles. So it might be interesting to try to apply your method to know the inequalities that hold between the Chern classes of vector bundles under some assumption, for example, very ample. Because you can use it in calculating Chern classes, you're very often allowed to use a splitting principle.
Yeah. So what is the question? So this is your comments or something?
Well, you know, I mean, you have this general method, general methodology, so maybe it could be applied to that. Your methodology, from what you're saying, your methodology has obvious weaknesses. For example, you can only do it assuming you've got vector bundles that are net, limits of ample bundles or something like this. And exactly the same thing applies if you're trying to prove Bogomolov inequalities in higher dimensions. It's just a suggestion you might think about.
Okay, so you mean we can also consider like vector bundles instead of dividers?
Under some special circumstances, I don't think there are, you know, you point out the similarity between your results and the Hodge index theorem. So in the Hodge index theorem, the analog of that for cycles on high dimensional varieties, nobody knows.
Yeah, okay, yeah. That's a good direction. Yeah, I think, yeah. I will try to, I will try to see. Yeah, thanks.
Okay, any further question or suggestion? So if no, let's thank Chen again.
Okay, thanks.
Okay, I think that's the end of today's talk, and also that's the end of the room part of this conference. So for those who will travel to Baltimore tomorrow, have a good trip, and we will see each other there. Okay.
Thank you.